let's talk about one-to-one and onto again. So suppose t is a linear transformation from v to v prime, and t inverse is a linear transformation from v prime to v. So first, one-to-one. Defined it above, but let me write it in a couple ways. So you'll see it in two different ways. You'll see it like this. So if v1 does not equal v2, then t of v1 does not equal t of v2. So in that case, basically it says if it has, from the domain, they have to be equal for the mapping to be equal. And that's one way to think of it. So another way to think of it is basically the contrapositive, which is always equivalent. So the other way of saying it is this: or if they're equal, so if t, I don't know why I keep moving that, I didn't used to do that. If t of v1 equals t of v2, then that implies that v1 equals v2. So that's the contrapositive. So the basic logic, and we haven't talked about this much, but if you have P implies Q, that is what we say logically equivalent to not Q implies not P, which I could talk more up to. Although just Google it and you'll find all kinds of examples of why the contrapositive makes sense and is logically equivalent. Then, so you've seen that before for one-to-one. It's a simple concept, graphically, mathematically. Just we got to have some well-defined notation, basically, is the only other thing. So notation-wise, you've seen this sort of thing before. You have a one-to-one correspondence like this. So if you map from A to B, we called it V to B prime. Then if you change it around and map back, you get the same thing. So it's one-to-one. So you can't have two different elements over here mapped to the same thing over here. Okay, then that would not be one-to-one. We know we can't have two, like one mapped to two different things, because that would not be a function in the first place. Okay, so this would be a not case, not one-to-one. Let's do onto. Onto you may not have heard about before. So onto, let me give you the definition. It says if V prime in V prime, then basically there exists, I'll just say it like this, so then T of V equals V prime for some V in V. So another way of saying that is the range of T is all of V prime. So there's a couple ways of thinking about this. Let me draw you the diagram again. So remember we had the range and codomain and all that, those concepts. Let's just do it like this so I can have the same size. So this is, let's just call this A. Oops, sorry. Just call this A and B this time. Because this is, both of these concepts, by the way, are not just for linear transformations. These concepts, definitions of one-to-one and onto, is true for any sort of function or mapping. So it'll go beyond just this course and linear transformations themselves. Okay. So basically, let's just go over what the statement is. So if v is in v prime, so we're saying we're putting a value or a vector over here. Okay, so basically means there exists something in v that maps to it. That means there has to be something over here that maps to it. So what you don't have is like, what you don't have is, what if you had like y equals x squared? Because we all know that kind of stuff. And that basically maps R to R positive. Loosely speaking, that's what it's doing. So if R is, the way we're writing it here, we're basically saying you're mapping R to R. I'm not going to change that. So you're mapping R to R. In this case, you don't get the whole thing. You get a subset of it. So there's elements over here that are not targeted by elements over here. Then that's not onto. So it has to map the entire set onto the other set. That's where the name comes from. So what we will see, another definition in a bit here, we'll see a couple theorems first, but basically, let's just state it so we have it. An isomorphism means a function is one-to-one and onto. So let me just define that. So isomorphism. So it would say something like this: a function, and let's just use a regular function, f that maps A to B is an isomorphism if and only if f is one-to-one and onto. So f is one-to-one, as we stated above, and all of A maps onto all of B. And that's going to be our definition or concept for if an inverse exists. So an inverse exists if and only if f is an isomorphism. You can map it back. We'll look at next theorem 3.8. And this describes when T is invertible. So T is invertible if and only if T is one-to-one and onto. So we got to show that proof, and we're going to describe a little bit anyway. I'll go through the proof of how you show something's one-to-one and how you show something is onto.